Chapter 6 is going to begin by reviewing functions. This is something that we went over a few chapters ago. So just a couple reminders. The first one is that functions have unique x values, and functions can pass the vertical line test. If you were going to draw a picture of a graph that represents a function, one way could be to draw a line as long as it's not a vertical line. You could draw a curve that is a smile or a frown. You could also draw one of these curves that goes on and on and on, and essentially all four of those examples pass the vertical line test, so they are functions. What we're going to start to do is we're actually going to start looking at inverses. So to find the inverse of a function, we're going to start by rewriting the function not using function notation. So instead of using f of x, I'm going to replace that with y. Makes things a little easier. That's the first step. The second step is to interchange the x and the y. So I'm actually going to rewrite this and replace the y with an x and replace the x with a y. So I'm just switching spots. And then the last step would be to solve for y. So I'm going to go through all of the steps that I would go through if I wanted to isolate a variable, and the variable I'm isolating right now is y. So after I do this, I'm going to have y equals 1/2 x plus 4. Right here, x over 2 is the same thing as 1 times x over 2, which actually can be written like that. So that's where my 1/2 x came from. And then 8 divided by 2 is 4. The last thing I would do is I would use what we call inverse notation to rewrite this, showing that this represents the inverse of our original function f of x. So this is ultimately what we were looking for. Now, it usually takes practicing this a couple of times before you become comfortable with it, but I do have all of those steps that I just described on the bottom of this page of notes in case you want to go back and review them. If you get stuck, you can follow these step by step and you will arrive at the correct answer as long as you are looking at those steps closely and doing what they're telling you to do. Let's go to the next page. So I want you to take a moment and find the inverse of this function. You can do this one of two ways. You can pause and try it on your own, come back, and then we'll go over it together. Or if you want to take the easy way in life, you can just not pause and watch me go over it and not learn a whole lot. So it's your choice. I'm going to go ahead and do what I did last time with replacing g of x with the letter y, interchanging the x and y, and then taking all the steps necessary to isolate my x. X minus 7 equals 1/3 y. If I want to multiply both sides by 3, that will allow me to cancel out that 1/3. So I have y equals 3 parentheses x minus 7. I can distribute and have 3x minus 21. And then the last thing I would do is write this in proper inverse notation to show that I know what I found was the inverse of our original function g of x. There are a few more examples here that I want you to try. This time, again, if you didn't already, then you definitely should this time pause the video and then come back and compare your answers to what I got to see if you're doing this properly. So go ahead and pause the video now. Okay, so I've unpaused. Here are my answers for A and B. I interchanged x and y, that's at that second stop, and then I took all of the steps possible to solve for y and rewrote it in function notation. This is just one way to express this. using function notation. There are other ways to rewrite this that are equivalent. So if you did different steps, that you still arrived to the same correct answer, but your steps are different. Just if you ever want to check, like what I would do is this: I would plug a number in for x, and then I would put that in my calculator to see what it's equal. And then what I would do is I'd put that same number in for your x and see if that is equal to what I got when I plugged that number into my x. And if it is equal, then it means however you decided to write this, they are equivalent. You'll know that it's correct. For b, again, it's pretty straightforward. I changed g of t to y. I solved for y. At the end, I rewrote this using proper inverse notation. Notice I had a g and a t there, just like my original. So that's a thing not to forget to go back and do that properly. Let's go to the next page. Okay, so we're going to start by describing a one-to-one function. One-to-one functions have unique y values. I'm sorry, I'm going to say x values because that's how we started it off last time. Unique x values and unique y values. I almost ruined the surprise. And so a one-to-one function, now, would you not just inspect the x values to make sure that they are unique? You would also have to inspect the y values to make sure those are unique also. So what we need to do in order to test a function to make sure it's one-to-one is now we not only do the vertical line test, but we have to do a horizontal line test also. And that just means that you take a imaginary horizontal line and you run it up along your function to make sure it only touches it one place at a time. And again, even though you've done it with a horizontal line, you still have to do it with a vertical line. And if it passes the test, then you would say, yes, this is a one-to-one function. For b, this is a function because it passes the vertical line test, but it is not a one-to-one function because it doesn't pass the horizontal line test. Not one-to-one. For c, this is an exponential function. It's going to approach 0 on the y-axis, and it's going further and further down. So this does pass the vertical line test. It also does pass the horizontal line test. It is a one-to-one function. I'm going to just put a yes. And then d does pass the vertical line test, but does not pass the horizontal line test. Not one-to-one. I've taken a class like this before in the past as a student, and there are a few things that I think are notable and important for you to know, but I don't necessarily want to have you take your time to do all this graphing to show it to you. But what we have here is a function. It's represented by f of x, which equals 2x plus 6. That is graphed. That is graphed as the red line. So I'm going to put a red line here. And then somebody found the inverse of this function for us, which is super sweet because it's a lot of work. And this graph is represented by the blue line. There is a relationship between a function and its inverse, and you may or may not see it, but the relationship is that the function and its inverse are reflections of each other over the line y equals x. And this is the line right here in black, and if you notice, if this acts as the mirror, these functions will line up as if they are being reflected through that mirror, y equals x. A function's inverse will be a reflection of the original over the line y equals x. Remember, y equals x is that perfectly diagonal line that goes to the origin and has a positive slope. I just want you to see one more time. Here's another example where I have an original function and its inverse, and when these are graphed, if they are truly inverses of each other, then they will be a reflection over that line y equals x. So you can kind of see that that is a true statement for this example here. In chapter 1, when we looked at a function, we calculated the cost to rent a 10-foot truck from U-Haul. And here's the equation for it. The U of M equals 0.79 M plus 1995. They ask what the input and output variables are. Hopefully input you're thinking miles, and output you're thinking cost of U-Haul. And they're asking you to find the inverse of this function. So going through all of the things that we've done in the past, I'm first going to write this without function notation. Then I'm going to go ahead and interchange x and y. And then I'm going to go ahead and solve for y. And after I solve for y, what I should have is x minus 1995 divided by 0.79. And then I'm going to write that in inverse notation. Now, a question like this, it's always possible to drive home this example that they would do this thing, this tricky little thing, where instead of writing inverse notation, they instead would kind of invert the function notation and make it small m of capital U. Because that is, again, another way. Oh, and notice up here, I needed to put m up here. Yeah. That would mean that you would, instead of plugging in a value for m, you'd be plugging in a value for u. And so that would look like this. U would be the input. They ask now, what are the input and output variables for the inverse? So now the input is cost, and the output is miles. And they ask you to find the cost to travel 100 miles. That is the m of, actually, let's go back here a little bit. That would be the u minus 1995 over 0.79 equals 100. And I would go through all of the processes here to solve for u and find out what the cost is. We can go ahead and do D and E, but these are kind of just examples to support that you can use inverses with everyday problems, and in a way they have a place there that fits into the world. Although I personally would probably not do things this way. I get that we're trying to drive home inverses and things like that, but I would probably never ask you to do it this way or have you do homework questions, but just be aware that it exists. Okay, so we have the domain and range of inverse functions at the end of this. And again, this is some information that is really interesting to know. For instance, our original function, the u of m, had a domain that was represented by 0 miles all the way up to 400 miles. So that is the maximum amount of miles you could drive in a day. That's the range of numbers. And then if you drove 0 miles, you would spend $19.95 all the way up to 400 miles, which would cost $335.95. That is the domain and range, the reasonable domain and range that go with this problem. If you were looking at the inverse function, you now would have a new domain because now the domain is represented by u and the range is represented by m. So notice that when you find the inverse, the range of my original becomes the domain of my inverse, and the domain of my original becomes the range of my inverse. It's almost like everything kind of gets flip-flopped to an extent. We're going to look at this a little bit more in the next video. A lot of this information is really just for your knowledge, not as much testable stuff, but just come into the next video and we will continue this conversation.